Today we are going to see the AVL trees. AVL trees or one of the binary trees. We could call it as upgraded binary tree. AVL means Adelson, V for I don't know his name, and L for Landis. So don't care about that. Those guys were built this AVL algorithm, and you have to focus on this algorithm. Yeah, and based on the AVL tree, we do all of the operations in login time. That's the best thing in the AVL, and it is a self-balancing tree. By using the some kind of a rotations and the balance factor. Yeah, it maintains a balance factor, which is um, height of the left side. I mean left child and height of the right child. It has to be realized between -1 to +1. If it is violated, then what we have to do is we have to either rotate left or rotate right. There is only two rotations in this, which means what we do. The height is 1 and I'm inserting the 2. Height is 2 and this would be 1, and the height I'm inserting the 3 again. Now the height is 3 and this will be 2 and this will be 1. But if you say this, it actually violates because the balance factor is here 0 minus 2, which means -2. Here what we can do is we could left rotate like this. Now the balance factor is 0. This is the left rotation. And if you'd like to see the right rotation, that is also same like the left rotation, but we're doing the right side. You know what? This is that. And this is called the right rotation. And in some situations, what do we do is, the situations like when for or these kind of trees, in these kind of branches, what we do is we first rotate this to right side like this, and after that we append to the parent node while backtracking, and after that we balance this is actually called as the double rotation. That's all. And these are all the rotations in AVL tree, and we're gonna see the practical part. And in the practical part, what we do is this is the RAM, and inside the RAM we're gonna insert 1 2 3 such that okay, let's see how it actually getting inserted in the RAM. We create a node and we insert and put it at a height is a 1 or 0. This is your choice. And after that, what you do is basically the left and right will be null. And if you want to insert the second node too, what you do is first you'll be here, and after that, by using the recursion, you go to the right side and you build that and put a height as 1. Now you backtrack and update the height as 2. And again, to build the third node, what you do is you will first see the 1, 2, and the 3. You build this. And after that, while backtracking, you update the height. It's 2, and here it will be 3. But here you will see that the AVL tree property is getting violated. At the time, what you do is just left rotate 2, 1, 3. Now you see the balance factor is 0. This is how we're gonna do that. I'm gonna use the Python. So you do in whatever language, whatever it is, the algorithm is same in all languages. So let's see the practical part now. We have to build a node along with the unique data, and the left and the right channel should be none for each node, and the height of each node has to be maintained as 1. Here, let's build the driver class. And the driver class created 2 methods, insert and delete. In the insert method, it's going to take 2 parameters, node and the data, to be inserted. And if there is no node, just insert that. Just build the node. Or if the data is less than the current node data, traverse left side. Or if it is greater than, then traverse right side to be inserted. Okay, after node inserted, we have to update the height of the node every time when we backtrack. So I'm going to create a get height that will take the node as a parameter, and if it's another node, we're returning the height as 0, and if it is a node, return the height of the node. So initially, at least one node's height should be 1, so I'm using 1. If it didn't use the 1, the initial height is 0. This is your choice. And we have to find the balance factor. So I'm creating the utility function called get balance factor. It also takes node, and if it's not node, we're returning 0, and otherwise we're calculating the balance factor. The formula is height of the left node minus height of the right node. And return the balance factor. That's it. Okay, now we get the balance factor, and if it is not balanced, we have to rotate the node. So let's build the left rotate function. It's gonna take a node, an unbalanced node, and the left rotation is basically the right side is going to be the root, and that's left is going to be the current node. The previous left is going to be the current node right side. After that, we're updating the height of the node. First, we have to update the node height, and after that, we have to update the root height because we're backtracking from leaf to the root. So we have to update the node height first and the root second. And next, the right rotation. It's also same like the left rotation, but we're rotating right side. Just change everything oppositely and written the final node. After build the left rotation and right rotation, we're gonna check whether it is realized between the -1 to +1. If it is less than the -1, again we have to check that whether we need to do the double rotation or the single rotation. Which means, you know what, the data is greater than the leaf node, then we have to do the left rotation only. Otherwise, we have to do the right rotation for the right node of the current node, and after that we have to rotate left. And if it is greater than the 1, we have to rotate right, similar to the left rotation that we just see. Right rotate, and if you want to do the double rotation, then left rotate the left of the current node and then right rotate the node to be balanced, and after that written the node. Next we're going to create the delete node function that's going to delete, that is also similar to the insert function but that deletes a node from the tree, similar to the insertion. I'm going to find and delete. Okay, if we can't find the node, then we're returning the node that we can't find it. If that is realized between the left side, then we're going to traverse left side to find the node. If it is greater than, we're traversing on the right side to find the node recursively. And once we find that, we're gonna delete those. After we found that, we're gonna delete them. If it is a leaf node, which is getting the right of that will be ours in none. So we're making the node as a none and written in none. Why we're checking left side is because, you know, the compiler will check from left to right. That's why we're checking the left side first. Okay, if you want to delete the root node, then we have to find the successor or predecessor of the node to be replaced and deleted with that. So I'm just doing the inner traversal to find the successor of that node. So this is the utility function to get that, and I'm simply returning that. Okay, so to get the successor, we're gonna replace the current node data with the successor data and delete the successor as a leaf node. And, you know, after delete the leaf node, the successor, we have to update the height while backtracking. So just copy and paste. But we don't have the data here while deletion. And so that we're gonna get the balance factor. We have to get the balance factor of the node of the right node. If it's less than, the single left rotation is enough. Otherwise, we have to do the double rotation. Now we have to right rotate the right node and we have to do the left rotation. And what we're going to do is now we're going to check in the RAM, in our memory, in our machine, that how it actually build the tree. Let's see that. And here what I'm going to do is I'm going to create the object of the driver class tree. Currently the root is nothing, which is none. And I'm going to insert first 1 to 5 elements. And let's see how to actually insert it. Okay, we're gonna see what's really happening inside our RAM and machine and how does the CPU work. Let's say we just build the AVL Tree algorithm. We're gonna first insert the first, which means we're gonna insert the element 1. I just debug, and first of all, we don't have a node, so we're just building that. Let's say we build the one node, and height is 1, left right is nothing. So if you want to insert the 2, we have to put the right of the first element node. We're referencing that and building that. And while backtracking, we're updating the height of that node. Did you see the call stack? It's getting popping off. Okay, we built the 2 nodes, fine. Cool. And we're gonna build the third node. Here's what's gonna happen is, what? Did you see the call stack? 1, 2. It's gonna build another call stack recursively, which another call stacks, another function recursively. Okay. After build, we're updating the height while backtracking. Did you see that? While violating the property of the AVL tree, we're rotating the nodes to be self-balanced. This is how this algorithm works. We built all the nodes fine. So we're just returning that to the previous one call stack as getting updated. In this way, the 4 and 5 elements inserted. And now let's here see in our RAM. In our memory, we built all of the nodes and heights are getting updated. This is how the AVL tree works. I hope you understand this. Okay, now we're gonna delete the node. First, I'm gonna show you how to delete a leaf node, and after that, I'm gonna show you how to relate a root node. Uh, yeah, the debug point hit. Here's a complete tree, and we have to delete the leaf node 5. Yeah, we're gonna delete the leaf node 5. So let's see how does this algorithm work. Okay, I'm in the delete node function, and similar to the insertion, we're gonna just find the node position and we're gonna delete that. Did you see that the call stack is getting increased recursively to find that? Recurse again, so we found that that is a leaf. So we're gonna make this as a none, which means we deleted that. And while backtracking, We are updating the height of each node to be self-balanced. And no need to rotate. Yeah, we deleted. There's no right, which means we deleted the element 5. We deleted the leaf node now. There is no 5 here. Now what we're going to do is we're going to delete the root node. This is also very simple, but yeah, it is simple. We're deleting the root instead of a leaf. And here we got a tree. Now we're going to delete the 2. We know we found that in the first iteration, which means the first recursion call. It is not a leaf. So we have to find the successor of that node to be replaced with that. The successor of the node would be 3. So by using the get successor utility, we're just finding out the third node. Yeah, we found that that is a third node. And we're returning that and updating the data and deleting the successor, which is the leaf node. We're going to delete the leaf node again, which means we have to delete the third node. Yeah. So I'm again backtracking to delete the node. So we're traversing. Yeah, we found that. That is a leaf. We're making that so none. We're deleting the memory reference. Yeah, we deleted. And while backtracking, updating the height. No need rotations. Everything's fine. And let's see now whether it is working or not. Mm, yeah, there is no node 3. We deleted that.